realize that a polynomial of degree n, say, this is a polynomial of degree n. N in x. This is a polynomial of degree n in x. When you carry out a division with, say, x minus alpha, when you carry out a division of this polynomial with x minus alpha, every time you divide 10 by 7, what does it lead to? It leads to a quotient plus remainder 3 divided by 7. Whenever you divide a polynomial by a linear polynomial, whenever you divide a polynomial by a linear, this is a linear polynomial, linear expression in x, then what results is a quotient qx plus a remainder r divided by x minus alpha. R is a number. See, every time you divide by a polynomial of degree 1, then the quotient would be of degree 1 less than the numerator. One more, 1 less than the numerator. If this was of degree n, then the quotient would be of degree n minus 1. The quotient of the degree of the quotient would be 1 less than the degree of the numerator. Right? If this is of degree 5, then quotient would be of degree 4. If this is of degree 2, quotient would be of degree 1. If this is of degree 20, then the quotient would be of degree 19. 20, so this would be 19. So, important thing is, if you are dividing by a linear expression, then the quotient is 1 degree less than the polynomial which is being divided. Right? And the remainder would be 1 degree less than the divisor. If the divisor is degree 1, then the remainder would be degree 0. Degree 0 is a pure number. 3, 4, 7, etc. These are pure numbers and they are said to be polynomials of degree 0. Pure numbers are said to be polynomials of degree 0. So, if you are dividing by a linear expression, then quotient would be degree n minus 1. Remainder would be a pure number. It would be degree 0. Now, when you carry out a division process, are you creating an equation or an identity? It's an identity. Division will lead to an identity. Quotient plus remainder by divisor, that's an identity. It's not an equation, it's an identity. R is the remainder when px is divided by x minus alpha. Right? Px. Then, so this is an identity. It's true for all values of x. This is true for all values of x. Px then is x minus alpha into qx plus r. Yes or no? When I multiply throughout by x minus alpha, this is what happens. Px is x minus alpha into qx plus r. Right? And this is also an identity. This is also an identity, yes or no? Right? If it's an identity, it's true for all values of x. So it is true for x equal to alpha also. It's true for x equal to alpha. If it's an identity, I can plug in any value of x on the left hand side. That will be equal to the corresponding value that I get on the right hand side for the same value of x. Let me plug in x equal to alpha on both sides. Then p alpha equals r, because this will become 0 on plugging in x equal to alpha. But what is r? R is the remainder when px is divided by x minus alpha. Yes or no? This is the remainder when px is divided by x minus alpha. When px is divided by x minus alpha, this is the remainder, right? P of alpha. That means value of the polynomial at x equal to alpha will be the remainder. Say if I have px, which is 3x squared plus x plus 1, right? And I divide this by x minus 2, for example, and I divide it by x minus 2, for example, then the remainder of this division will give me, first of all, this division will give me two things. Qx, which is 1 degree less than the numerator, which would be a degree 1, plus a remainder r by x minus 2. How do you find the remainder? The remainder r, when you divide px by x minus 2, would be p of 2. That means value of px at x equal to 2. That means the remainder would be 3 into 2 squared plus 2 plus 1. So this is 12 plus 2, 14 and 1, 15 would be the remainder. When you divide 3x squared plus x plus 2 by x minus 2. Yes or no? You can check that with the help of long division. You know how to divide, right? This long division, 3x squared plus x plus 1. When you divide by x minus 2, you know how to do this division? So first you will do like a 2x or 3x. So 3x will be like 3x squared minus 6x. Then you subtract, so 7x plus 1. And then you do a plus 7, right? 7x minus 14. And subtract, eventually 15 is the remainder. 1 minus minus 14, this gets cancelled when you subtract, right? 15 is the remainder. You didn't need to do a long division to find the remainder. When px is divided by x minus alpha, the remainder r would be the value of px at x equal to alpha. Yes or no? Right? Do you all understand this? Huh? This essentially is what is referred to as remainder theorem. I have covered this in the past, isn't it? Now, the important thing is in context of polynomials. If px is divided by x minus alpha, the remainder is p of alpha, value of px at x equal to alpha. Now, can I wipe this off? If it so happens, if p of alpha is 0, what is p of alpha? P of alpha is the remainder r when px is divided by x minus alpha. That means the remainder is 0. Right? P of alpha is the remainder when px is divided by x minus alpha. Now if the remainder is 0, that means if the remainder of this division is 0, that means px is divisible by x minus alpha. Px must be, see, if p of alpha is 0, that means the value of the numerator at x equal to alpha becomes 0. That means the remainder is 0. And if the remainder is 0, that means px is perfectly divisible by x minus alpha. Px is divisible by x minus alpha. It means that x minus alpha must be a factor of px. X minus alpha must be a factor of px. That means px can be written as x minus alpha into something. Px can be written as x minus alpha into something. Yes or no? Right? Isn't it? That means if x minus alpha is a factor of px, that means px can be written as x minus alpha into something. This is what it means. Something means this will also be a polynomial. This will also be a polynomial. Px divisible by x minus alpha means when you divide it by x minus alpha, you must still get a polynomial. You must still get a polynomial. So px by x minus alpha, if it turns out to be a polynomial, that means px is divisible by x minus alpha. And when would px be divisible by x minus alpha? If p alpha is 0. P alpha equal to 0 means what? Alpha is a root of px. This is what it means. Alpha is a root of px. This is what it means. Yes or no? If p alpha is 0, that means alpha is a root of px. That means if alpha is a root of px, px is divisible by x minus alpha. X minus alpha therefore will be a factor of px. X minus alpha therefore will be a factor of px. That means if alpha is a root of a polynomial, px, then x minus alpha certainly must turn out to be a factor of that polynomial. Yes or no? That's important, isn't it? If P alpha is 0, that means if alpha is a root of a polynomial which you have obtained, let's say by inspection or by some other means, you figured out that this polynomial is vanishing at x equal to alpha, then you can conclude that P alpha 0 means the remainder when Px is divided by x minus alpha is 0. That means Px is perfectly divisible by x minus alpha. That means x minus alpha must be a factor of Px. That's important. Yes or no? Right? Now, can I wipe this off? And every time you factorize a polynomial, are you creating an equation or an identity? You are creating two identical polynomials. One factored, one unfactored. Yes or no? Now, see, the important thing is, if a polynomial Px, which is say a naught x power n, this is a polynomial of degree n, right? A1 x power n minus 1, a2 x power n minus 2 plus an is a polynomial of degree n. So what can't be 0? A naught. A naught can't be 0. Because others could be 0, but a naught cannot be 0. A naught cannot be 0. Right? Now, it's a polynomial of degree n. For how many values of x will it vanish? N values. It must have exactly n roots. Exactly n roots, real or complex, distinct or coincident. Say, let me call those n roots as alpha 1, alpha 2, alpha 3, alpha n are the n roots. Some of them could be real, some of them could be complex, some could be coincident, etc. Don't bother about that, right? It must have exactly n roots. That means this polynomial will vanish at x equal to alpha 1, will vanish at x equal to alpha 2, will vanish at x equal to alpha 3, right? That means the value of this polynomial Px at x equal to alpha 1 must be 0. The value of this polynomial at x equal to alpha 2 must be 0. The value of this polynomial at x equal to alpha n must be 0 because alpha 1, alpha 2, alpha n are all roots of this polynomial. They are all roots of this polynomial. Yes or no? Right? Isn't it? Now, did I tell you, if P alpha is 0, if alpha is a root of the polynomial, it means that x minus alpha must be a factor of the polynomial. This is what I told you. Now, if P alpha 1 is 0, it means that x minus alpha 1 must be a factor. This means that x minus, if P alpha 2 is 0, it means factor of Px. It means x minus alpha 2 must be a factor of Px. This means that x minus alpha n must be a factor of Px. Yes or no? Do you all understand this? That means when I factorize Px, x minus alpha 1, x minus alpha 2, x minus alpha n must all appear as factors, must all appear as factors of Px. Right? Yes or no? Can I just remove this? Have you registered this idea? Which means Px, which is a naught x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus an can be factorized as, will have factors like x minus alpha 1, right, must be a factor of this. X minus alpha 2 must be a factor of px, like we've discovered. X minus alpha 3 must be a factor. X minus alpha 4 must be a factor. X minus alpha n must be a factor of px. These must be factors of px. Yes or no? When you factorize something completely, you are expecting to produce an equation or an identity? You are expecting to produce an identity. Now the important thing is this is a polynomial of degree n, this is also polynomial of degree n. See, x into x into x into x into x. The highest power of x is n. So this is also polynomial of degree n in x. Yes or no? This is also a polynomial of degree n in x. But is this polynomial identical to this polynomial? Yes. Look at the coefficient of x power n. Is a naught here? But what's the coefficient of x power n here? X into x into x into x, x power n. 1 into x power n. So coefficient of x power n on the right hand side is 1. Whereas the coefficient of x power n on the left hand side is a naught. Yes or no? So they are not identical yet. Although you have produced factors here, but you have not produced an identity yet. To make coefficient of x power n a naught on the right hand side, you multiply the right hand side with a naught. Now coefficient of x power n on the left hand side is a naught. Coefficient of x into x into x, x power n on the right hand side will also be a naught. Yes or no? Clear? So if a polynomial is like this, a naught x power n plus a1 x power n minus 1, and alpha 1, alpha 2, alpha 3, alpha n are roots of the polynomial, then that polynomial could be factorized as a naught, which is coefficient of x power n into x minus alpha 1 into x minus alpha 2, x minus alpha 3. Now the left hand side is identically equal to the right hand side. Now we have produced an identity. Yes or no? Right? Say for example, if I have a quadratic polynomial, say ax squared plus bx plus c, right? And if alpha and beta are the roots of this quadratic, that means p alpha must be 0. The value of this quadratic at x equal to alpha must be 0. That means if p alpha is 0, it means x minus alpha must be a factor of px. Yes or no? X minus alpha then must be a factor of px. If p beta is 0, it means x minus beta must be a factor of px. Yes or no? Now if I choose to factorize this, given that alpha beta are the roots of this, now if I choose to factorize this, then I know that x minus alpha must be a factor of this expression, x minus beta must be a factor of this expression. That's why this expression vanishes at x equal to alpha and x equal to beta. But is this identically equal to this? No, because coefficient of x square is a here and the coefficient of x square is 1 here. So I multiply by a both sides so that I can create an identity. Now it becomes an identity. The left hand side is a polynomial of degree 2 identical to the right hand side, which is also a polynomial of degree 2 in x. Yes or no? Do you all understand this? Now, having said this, so this is identical, and if it's a quadratic, a should not be 0. And if a is not 0, can I not divide both sides by a? A cannot be 0 because it's a polynomial of degree 2. If a were to be 0, it will become a linear polynomial. So a should not be 0. A not 0. And if a is not 0, I can divide by a both sides, right? That means if I divide by a both sides, I get x squared plus b by a into x plus c by a equal to x minus alpha into x minus beta, where alpha and beta are what? The roots of this quadratic. This quadratic will become 0 at x equal to alpha, at x equal to beta, and at no other point. At no other value of x will it become 0, right? Because a polynomial of degree 2 will have exactly 2 roots. Will have exactly 2 roots. Yes or no? Now, this is an identity. This is a polynomial of degree 2. This, when you multiply, you see this is x squared minus x into alpha plus beta plus alpha beta is what you get when you multiply. Yes or no? Now these are identical polynomials. See, coefficient of x square is 1 here. Coefficient of x square is 1 here. The coefficient of x here is b by a. What is the coefficient of x there? Minus of alpha plus beta. Coefficient of x here is minus of alpha plus beta. So minus of alpha plus beta. What is the constant term here? C by a. What is the constant term there? Alpha beta. So equating coefficients of equal powers of x, this is what I get. So this gives me alpha plus beta equal to minus b by a, sum of the roots, which you know, and alpha beta equal to c by a, the product of the roots. Yes or no? Do you precisely understand everything that I have said here? No confusion, right? Coefficient of x here is minus of alpha plus beta, and the constant term is alpha beta. So you can find the sum of the roots and product of the roots without knowing the roots. In a quadratic, right? You can find this was a quadratic, sum of the roots. You didn't need to know alpha beta to find sum of the roots, minus b by a. You didn't need to know alpha beta to find the product of the roots, c by a. Yes or no? Now, stand by.